Welcome everyone to NOVA 77's webinar on data and AI. I'm a student volunteer at NOVA 77 and I will be your moderator today. My name is Steve. Today's topic is on General Adversarial Networks or GANs by Alex Cui and Erich Liang. Am I pronouncing those names correctly?
Yep, you're good.
All right. Alex Cui is a fourth-year undergraduate at Caltech in computer science and data science. He is an impact-driven machine learning researcher, engineer, and creator in the field of autonomous vehicles, computer vision, and computational chemistry. Previously, he's worked at Uber, ATG, Facebook, and two Y Combinator startups. Erich Liang is a recent graduate from Caltech, holding a double major in computer science and math. He enjoys tackling challenging and useful problems, especially in the fields of machine learning and computer vision. Previously, he has worked at companies such as Facebook, Microsoft, and Bloomberg, and has also done research with professors Katie Bauman and Adam Weirman. Welcome, Alex and Erich. During the Q&A session, visitors can submit questions, and then I will go and peruse those questions and read aloud the questions, give them to the speakers, and wait for the replies. And we'll just go on a rolling basis with questions. You can submit them at any point in time. And then when the speakers open up the questioning period, I'll just ask them. So without further ado, Alex can take it away.
All right, thank you so much, Sahi. So we're really happy today to be presenting to you guys having been hosted by Cui and AI as in addition to NOVA 77. And so we're really excited to talk about our project Juntos, where we're trying to bring families together one photo at a time. And yeah, I guess we'll jump into it. By the way, there is the link to the PowerPoint presentation over here if you want to follow along and click the links that we have. I think I'll just drop that into the chat too, so then people don't have to, yeah. Okay, great. And recording. As Sahi said, this is who I am. I think she covered everything, but yeah, Caltech class of 2021. And here's some of the companies I worked for before. And here's some of my research interests. And next year, I'll be doing research masters at University of Toronto, working on autonomous vehicles.
Hi, everyone. Once again, I'm Erich Liang, currently recent graduated from Caltech with computer science and math. Here's some companies I've worked at as well. And next year, I'm planning on starting my PhD at UC Berkeley, working on computer vision / human vision related problems. So yeah, we'll see how that goes. And yeah, so I guess next slide. Yeah, and so today, here's a quick outline of what we're going to be covering. So first of all, we'll be talking about the motivation for Project Juntos and why we built it. Afterwards, we'll dive into some technical details. So we'll give a quick crash course on generative adversarial networks, or GANs for short. We'll also be talking about transparent latent GANs, which is a slightly modified version of the basic GAN. Afterwards, we'll talk about Juntos specific modifications we made to the transparent latent GANs themselves. And then finally, we'll wrap up with a little discussion about future work for Juntos, how to apply GANs to your work, as well as a little bit of Q&A. So yep, let's get started.
All right. I'm going to start by describing kind of the driving question that made us want to pursue GANs, because with every problem, there's like suitable and not suitable technologies, and it's important that you're actually doing motivating your solutions from like problems you can see in the real world. So our core question is, how can we generate photos of people from description alone? This is as common to just trying to describe what your friend looks like, to trying to do some sort of investigation. There's multiple applications where it'd be really convenient to have this kind of photorealism. One example of this is helping children to identify their parents. And so this was actually a pretty big deal 4 years ago, and it's still a big deal now, which is that there are many children who are separated from their parents at the border of like the United States and Mexico. And while many of their parents are sent back to south of the border, oftentimes children are detained at the border and without very many resources. And so a question that we wanted to answer was, can we create an easier way for people to be able to find, like to create for example, photograph of their parent when they didn't have a physical one, and use that to help people search through a database, like let's say of NGOs to attempt to make this kind of match. Secondly, as you can see here, we have kind of a comical but actually real world example of a forensic sketch. And so this is a big application where, let's say a crime happened and there's no video recording of the perpetrator, then it becomes important to try to get both a scalable solution and also a solution that's less biased by human judgment, and regenerating what like the perpetrator looked like, and using visual feedback and cues from the victim in order to refine the output. And finally, I'll let Eric expand on this.
Sure. Yeah. There's one thing that's sort of interesting to keep in mind is that the photos that we're trying to generate aren't necessarily have to be two-dimensional, and they can actually be three-dimensional as well. So for example, if you're trying to create some sort of like character or avatar in a game that has 3D rendering, the process might look something like this, where on the left-hand side, you have a menu where there's a lot of different toggles and knobs that you can sort of control to describe the character you want to create. And on the right-hand side, we see the character being rendered. And what's interesting here is that currently the games are doing this by sort of pre-computing a lot of the different attributes that players can control. And so essentially what's happening is the game just takes the currently selected attributes that are pre-computed and stitches them together to form the avatar. But one downside of this is that because all these attributes are pre-computed, there's naturally a limit on the number of distinct avatars you can create. And in addition, not all of these attribute combinations look realistic. So for example, I could easily give this person gray hair, but then red eyebrows, which isn't really realistic. And so if there's a way to sort of generalize this model creation process so that it doesn't rely on pre-computed attributes, but it also looks more photorealistic, that could be also very interesting and useful as well. So now that we've seen a couple examples of photo generation problems, there's a couple key underlying factors that sort of tie all of them together. So first of all, the question is, how can we make sure that the photos we're generating are looking realistic as much as possible? Second of all, how do we get control of the photo generation process so that we're able to customize these photos to match a certain set of descriptions or expectations that we have? And finally, how do we make sure that photo generation is fast and scalable as well? And so in order to help deal with this, we have a couple of solutions here. First of all, we have generative adversarial networks to help with the realistic part of the problem. Next, we have transparent latent mapping, which is a technique that can help with the customization of these photos we're creating. And finally, to make things fast and scalable, we have GPUs, which is often used to make machine learning much faster. And as an added bonus, the GANs that we're using, or generative adversarial networks, make it so that we don't have to pre-compute a lot of these different attributes or descriptions, which is an added bonus. So before we sort of dive into the details of all these methods, though, we're going to show you Juntos, which is an excellent example of how, when you mix all these elements together, like what's possible. So Alex will go ahead and do that.
All right. Yeah. So here we start with the initial dashboard. So say we want to create a portrait. So I'll just move it slightly to show you. This is kind of our like 0, 0 face that we're generating. So it isn't like biased in any one way. And so first, let's play around with it. You can try to adjust it to be more masculine or feminine. let's say we want it to be older as well. Okay, so go to next. Let's say we want to have like a slightly darker complexion. And then, I don't know, let's say we wanted to change the nose size for whatever reason. These are all things that we can edit, and it tries to keep the image as similar as possible while only changing that part of the attributes. So next, let's maybe lower the hairline, increase the grayness, and then also increase, let's say, the lightness of the color of the hair. Cool. So now we can try to, bump up the amount of bangs, although there's plenty already, and then also try to increase the straightness of the hair. All right. So next, there are things that we can edit, like beard, no beard. This mostly works for like the male outputs, but something we can definitely edit is like eyeglasses. So put on cool shaded glasses, and there you go. That's the generation process. So that's a little demo of Juntos, and if any of you guys have questions, let me know. And in the later slide, we'll be posting a link to the web demo as well. Okay, let's see.
It's buffering. One moment.
Right.
Great. So now that we've seen Juntos in play, let's talk about how it works. And to sort of first understand what's going on, we need to talk about GANs. So GANs actually is short for generative adversarial networks. And so this is essentially an unsupervised method that tries to generate data which mimics some sort of input data that's given to the GAN at first. And so, for example, if we have a GAN that we feed in a lot of images of, like, let's say, real life images of dogs, we might expect a GAN to sort of be able to output images that look like real dogs as well. And so the way that GANs sort of make this happen is that GANs have two parts to them, which are pretty much at all times with conflict to one another. So the first part is something we call a generator. And the goal of a generator is to sort of generate synthetic images that hopefully mimic the input data as much as possible. And the other part of a GAN is something we call a discriminator. And so what a discriminator does is it's trying to distinguish between the real images, which come from the actual input data initially given, and the synthetic images, which are coming from the generator itself. And so what's interesting here is that because the GAN has control over both the generator and the discriminator, what it's trying to do is it's trying to improve its generator based off of its discriminator, and it's also trying to improve its discriminator based off of the generator. And so one nice way of thinking about a GAN is like it's kind of like a robot that's trying to play soccer against itself. So we have on one hand the discriminator, which sort of functions as a goalie. It's trying to guard a goal that's filled with actual real images from the input data. And on the other hand, we have the generator, which is essentially the player trying to take shots, and it's trying to essentially make sure that the synthetic images it's sending at the discriminator gets past the goalie and gets mixed up with the real images itself. And to sort of help make things a bit more concrete, here's a sort of diagram of what a GAN might look like. So in the bottom left corner, we have the generator, which has the function of taking random noise, and it's trying to generate synthetic images from it. And one interesting thing to know is that it actually has no idea what the original training set it's supposed to emulate actually is, since that's not fed into the generator. Now, on the other hand, on the right side, we have the discriminator in red, and the discriminator's task is to read in the input data that's initially given, as well as the synthetic images from the generator, and it's going to output a label of either real or fake. And typically the generator and discriminator are both neural networks. And as you may know, neural networks can use a method called backpropagation to improve their performance as well as their accuracy. And so what again we'll try and do is by sort of using the generator and discriminator and backpropagation together, it'll try and iteratively improve both pieces of itself as much as possible. So after many iterations of this sort of training, the hope is that we'll have a very skilled discriminator, but we'll also have an even more skilled generator, so that when the generator sends its images mixed in with the training data set, the discriminator will only be able to apply the correct label of real or fake roughly 50% of the time. And at this point, we can be pretty confident that the generator is doing a good job of generating images that are very similar to the input data set, even though it has no idea what the input data set looks like itself. Now, some of you may be wondering, what is this random noise doing? Like, how is this generator even able to create like any image from simply random noise, even let alone like images that look like the training data set? And in order to sort of understand this, we need to understand the concept of a latent space. So in essence, a latent space is essentially a representation of compressed data. So here's an example of a data set that I might have. So as you can see here, I have 3 images of different chairs. So let's say I'm trying to create a chair latent space. So something I can do manually is I can take a look at each chair here and write down some numerical values that describe each chair, such as number of legs, width, rotation angle, and color. And so the idea here is that even though I'm only using a couple of numbers and letters to describe each chair, I'm essentially capturing the essence of each chair here. So as you can see, each chair in the left has been represented as simply 4 different values on the right, with each chair represented as a row here. And so what we can do with this representation is if we simply take the sort of values that we've written down about each chair and treat them as coordinate values, we can actually sort of plot these individual images, which we had before, which are very complex, and simply represent them as different points inside this high dimensional space. And so in this way, each image in our original data set is actually represented as some sort of vector. And so this is something we call latent vector. And what's interesting about this is by doing this, we're able to essentially sample random images using random noise now. Because if you consider a random point sampled from this high dimensional space, as long as we have access to some sort of function that's able to interpret each value at each coordinate and convert that back into a chair, sampling random values now becomes a theme of sampling random images, which is exactly what we wanted. So, yep. Alex, I think you're muted, by the way.
Yeah, thanks. Thanks for that, Eric. So given all that, we now have a pretty powerful tool in GANs. However, if you notice something, is that we still have one shortcoming. And so this work attempts to address it. It's called the Transparent Latent GAN, or the TL GAN, by Xiaobo Guan. And I have some links there to an online demo in their GitHub. So one problem is that we actually learned this latent space, but we don't know what each dimension actually correlates to. And so in the chair example that Eric brought up, we knew one dimension was angle, one was like color, but in this case, they could be any permutation of dimensions. And what we're trying to deal with now is how can we generate a specific image with a GAN? And so this is what the TL GAN attempts to address. So I'm going to walk through how they do this. And like basically what we achieve at the end is an ability to take the attributes we want. Let's say, no mustache, brown hair, no glasses, create the appropriate latent vector, and then create the appropriate portrait. Let's see. I'm going to see if I can get a laser pointer here. Yes, perfect. Great. So first, let's assume that we have a data set that correlates images to these labels. So let's say they're labels describing a face. So the first thing we want to do about this process is actually just create a classifier for each attribute. So given some data set, and here we're using a celeb A data set, let's try to, so it's a data set of celebrities. Let's try to classify this image into the appropriate labels. Next, we want to train a GAN. And so in this particular instance, we're using a progressively growing GANs. So I'm going to abbreviate to PGAN. It's just like a type of GAN. And so this will turn our random noise. Here I have it as a 2D, but you can imagine just this is our random lane vector, and turn it into the appropriate images and try to make them as realistic as possible. Next, this is actually kind of where the magical step is, which is we want to find out, like, given this, lane space that encodes these elements, such as mustache, brown hair, glasses, we want to find out where the vector of, let's say, mustache is in this lane space. And so we can do this by creating our own data set. What we do is we sample random lane vectors, we create images, and then we feed them through the classifier. Now we get a mapping between lane vectors and attributes. And so we have this data set of these XZ pairs. Now we actually introduce this latent map. So that will allow us to go backwards from the labels to the lane vectors. And so what TLGAN does is trains a generalized linear model, but you can plug in your favorite deep learning model here, and essentially tries to find this correlation between this attribute space, which is maybe, let's say, 40 attributes, to the lane vector space, which is maybe 512 floating point numbers. And so just to give you an example of what this could look like potentially is, imagine that our lane vector space is very simple and actually correlates very well with. And so, as Eric gave in the chair example, in the same way, we're basically trying to find out, given where is that star, the appropriate star that's going to encode like the attributes we want for this image. And so we're essentially trying to get to this vector over here. Cool. And so overall, that's the training pipeline for the TLGAN. Now, what we're trying to create images. We just rearrange the steps a little bit. So we start from the attributes space, and then get the images as an output. Let me know if there's any questions about that. Okay, just always feel free to email us or the chat, and we'll try to get back to you. Now I'll let Eric take it away.
Yeah, thanks. So now that we've seen roughly what TLGAN does, let's talk about what we did specifically during to build Juntos off of TLGAN. So if we go next. Yeah, so first up, TLGAN was originally trained to generate celebrity faces. So obviously this is very close to what we're looking for. We're able to generate realistic looking human faces with all these different attributes, which is great. But if you recall, the original idea behind Juntos is to sort of help reunite children with their family members, and not everyone's family members an actual celebrity. So as a result, we sort of need to be able to generate images sort of outside of the scope of what TLGAN is currently able to do. And so this involves trying to use a new data set, but also a little bit of retraining as well to actually make sure that everything still works as properly as possible. So, yeah, so one of our first steps was to find a new data set with faces that are much more, I guess, around the mill, not all celebrity faces. And so something we were looking at was the Flickr data set. As you can see here, there's a large variety of many faces and many different situations and poses. So this is like a nice and beefy data set to use. And the way we're able to sort of use this data set in the middle of all this complicated machinery takes a couple of steps and a little bit of thinking to do. So here we have a diagram of the modified version of TLGAN, which we ended up using. And so the first thing we did was to replace PGAN with StyleGAN. This is one of the crucial steps here because PGAN was essentially trained with those celebrity faces. And so basically PGAN knows how to map latent vectors or random noise to celebrity faces, but not the normal faces. So in our case though, we happened to find StyleGAN, which is trained with the Flickr dataset that we were trying to use. So we first replaced PGAN with StyleGAN to get this sort of new latent space to image mapping. Afterwards, we tried to also have a new latent map as well. The reason why this is necessary is because StyleGAN and PGAN probably interpret this latent space very differently. And so in order to make sure we still have proper control of how images are being generated, we need to retrain our latent map. And so to do this, we take the images from Flickr and we use the original attribute classifier, which tells us information, physical information that we can actually see from each face. And using that, we're able to generate our new X prime and Z pairs to sort of retrain this latent map. And so using this, we were then able to sort of essentially hack our way into TLGAN and replace the original data set with something that was more appropriate for our purposes. And then we ended up deploying this with Node.js and RabbitMQ. And then finally, to sort of round things off, we also try to constrain our latent map to avoid unrealistic faces, which we'll actually talk about a little bit more later. Yeah.
All right, so here I'm just going to step through a little bit in more detail what the retraining looks like for Juntos. And so here's the original training pipeline for the TLGAN. And as you can see, here's the new training pipeline. And so the dotted lines indicate things that we've replaced, whereas the attribute classifier has stayed the same. And so as Eric was alluding to, here, the biggest part kind of mentally is that, you know, we'll talk about this later, but we accomplished this at the Stanford Hackathon. And to do this, you know, we weren't able to retrain a huge expensive GAN. And part of that is because these things actually take days, if not weeks, to train on expensive GPUs. And so being able to plug in a new one and was very essential to us. And that's one of the advantages of this framework. So plugging in the new GAN, we were able to recreate a new data set. And this is in part because, you know, these latent spaces, essentially every time you learn a new GAN, they, like let's say the first dimension or the fifth dimension will correspond to a completely different thing in the image space. So that's what was step one. And then fast forward to step 4, we again do this new latent map training, which is very cheap and efficient. And so something like this, we were able to do in only a few hours on you know, one of the most basic like Amazon GPUs, because we don't have to go through the costly step of going into the image space, which is really huge. You know, let's say 200 by 200 images, already tens of thousands of dimensions, whereas this goes from a 40 dimension to 500 dimension process. And then finally, we just use these new latent maps and StyleGAN in order to get the same inference pipeline that we wanted.
Great. So now that you've sort of seen an overview of how Juntos works, let's talk about some next steps and improvements that we could have made on top of Juntos with more time. So the first question and issue we want to talk about is something called attribute entanglement. So intuitively, you can think of it as this. If I have, let's say, a current image right now, and I'm only changing one attribute, for example, hair grayness, in this case, when I change the hair grayness to be minimal, the face actually looks younger as well. But when I change hair grayness to maximum, the face looks older as well. And at first, this looks like it's not too big of an issue, but if you play around with Juntos, we actually do have another scroll bar that controls age as well. So currently, by changing one attribute, we're actually impacting what the other attributes kind of appear as well. And so in order to sort of tackle this issue, which might cause to be a bit harder to recreate faces you want, one idea is to sort of take a look at the latent vectors that specifically control each attribute. So you can think of like each face as one point in the image space, and depending on how many copies of each vector we add, that's how we sort of modify that image for that sort of attribute. So at first, we'll have a first iteration of these different latent vectors that correspond with different attributes that we want to change. But what we can actually do is, instead of directly using these learned vectors, we can take the orthogonal components of each vector with respect to the other attributes. And intuitively, essentially, if, for example, if we're, instead of using the orange gray hair vector, and we use the blue gray hair prime vector instead, now when we add copies of the gray hair prime vector to our image, that will probably not impact the age direction's value as much anymore. And so by doing this multiple times and essentially making sure our vectors for our different attributes are essentially as perpendicular as they can be, we can sort of reduce the effects of this problem. Another interesting side effect that we saw is that it's actually possible to create sort of exotic faces that are sort of out of domain. Obviously these do look a little bit realistic, but upon closer inspection, things look a little bit off as well. And so the question is, why are these faces still up here? And so one idea I guess like a way to sort of understand like why this might happen, take for example, a sample attribute that might be like long hair. So as we know, attributes are represented by vectors in the latent space. So for now, let's just say each time you add one of these vectors to your face right now, the length of the hair of the face will grow by 1 centimeter. So one thing to note, though, is that vectors can span infinitely in both directions, both positive and negative. But oftentimes, attributes don't have this rare property. So for example, for a face that has, let's say, 40 centimeters worth of hair, the face looks quite natural and looks okay. When we go down to the extreme of 0 centimeters, which is bald, the image starts to sort of deform a little, but you can sort of see that like this person is a bald person. But then, if I just add a bunch of negative versions of my vector for long hair, it's possible to sort of try and generate an image with negative hair length, which clearly isn't really possible in the real world, but it's definitely possible within this latent space. And so as a result, by sort of setting these extreme values on a lot of these images, sometimes you are able to create out of domain images, even though the other images that you can create look quite realistic. And so one way to avoid this problem is to actually sort of truncate or bound the latent space itself in order to sort of make sure that we don't get these sort of out of domain images. And this will sort of take some analysis by hand to sort of interpret what exactly is a realistic attribute, what are its possible lengths, and then sort of truncating the latent space based off of that. Oh, Alex, I think you're muted.
Yeah, thanks, Eric. So another feature that we're really interested in computing is like trying to make it so that it's easy to import, let's say you or my face into Juntos, so that we can customize it essentially. So if you see here, this is an example. This feature is still like very much in beta, but what I did here was I tried to take my face when I had much shorter hair and try to map it to a face in Juntos that I could customize. And so this is currently what we get. So it's not an exact match, but also not too far. And so how do we do this? Well, you remember this is what Juntos is now. We go from attributes to images. But actually, we can go from images all the way back to images, doing the complete loop by essentially looking at an image like this and mapping it to attribute space. This literally just means trying to classify, do I have a mustache? Do I have dark hair? Do I have makeup, et cetera, et cetera? Like what is my skin tone? What's my age? And so by doing this, we can get a pretty crude estimate of like where I am in the feature space, and then where I am in the lane space. And so this is, obviously there are actually a lot of GANs who try to go directly from the images to the lane space, which would be a little bit better because then you don't get this like loss of data essentially by going from, instead of 500 dimensions to 40. So at the same time though, this is very cheap and doesn't require another huge GAN. So definitely one advantage of the approach.
Cool. Thanks, Alex. So yeah, I guess so. Now we'll start talking about how we could potentially apply GANs to your work and our experience working with GANs as well. So I guess as a bit of context again, Juntos was actually created within a span of 36 hours with me, Alex, and 2 other very talented team members. This was actually built at TreeHacks 2019, which is a hackathon held at Stanford. And even though we were able to sort of achieve the best deep learning hack and all that, by no means did we create like a novel architecture, publish a paper and all that. There's certain things you sort of need to take into consideration, especially when you're working under time pressure with GANs. And so something we sort of recommend when you're trying to get started initially with GANs, as well as when you're under time pressure, is to try and find as many pre-trained models and existing data sets as possible. For a lot of those who may have had previous experience with machine learning, especially for like larger models, those might take a long time to train, a long time to tune properly. And so that's something you might want to try to avoid with pre-trained models. And also collecting data is very important. And so within like a short time constraint, that's not very feasible at times. So instead of trying to do all of this from scratch, try and borrow as much as possible, and then try and fine tune smaller bits of the model instead. So in this case, what we did was borrow a lot of the architecture and a lot of the attribute classifier as well. That was one of the key parts of Juntos. And the only parts we tried to retrain were the simpler parts, such as like the linear models, which take much less time to actually get right. And so that's something we would definitely recommend if you're trying to get started. And over here, we've had a few other resources listed out. One is Papers with Code. This gives you an excellent source for data sets, as well as different methods used on different data sets. So you can start to get started with that. Google Colab is great for computation on smaller scales. And then the last link down below is actually a link to, I think, StyleGAN 2 ADA, which is improvement upon the original StyleGAN we used for Juntos. So that's a nice out-of-the-box GAN if you want to start looking at that.
Yeah, thanks, Eric. And so just to continue on, purportedly only requires to train the GAN using a data set of a few thousand images. Unheard of, given that previous GANs had to use pretty large data sets of tens of thousands of images. And so this is really exciting new developments in the field. So if you wanted to scale up, refine your GAN and also be able to host it online, it's definitely a whole process, but some of the main points is, finding a way to generate a data set, because something that's customized will definitely perform better in your use case. So, one example is, even if your application was to make an app that ran on a cell phone, you have a database of cell phone images ideally, as opposed to images taken by professional cameras. Secondly, you'd want to train your model. So whether it's with GPUs, cloud services, or even Google Colab, which is a free service that can get you pretty far, that will be important. However, as I said, new style GAN still requires actually a GPU compute time to train one model. Terrible. You might want to find those shortcut ways that we were talking about to get there. And finally, you want to deploy your model. For us, we deployed it as an API with our Python Flask. So that allows us to call it from any simple web interface. Sources. So any potential users could run it on Colab for free. And then finally, so this is one other thing that we wanted to note, kind of on the ethical concerns of GANs, in addition to like bias. And so, as you guys all know, there is definitely in all of these image data sets, and that often they work much more accurately or familiarly with very well represented in the data set, as opposed to people who can see that from our example, and the original data set that TLGAN was trained on. And so you can see that there's many sources of bias, not only from the types of, let's say, people in your data set, but also, what kind of online service did you scrape the data set from? And in the original paper, they described actually doing a lot of, how do you know, like, what you're filtering for doesn't bias your data set as well. And so there are many approaches. The first one is obviously trying to collect a more diverse data set, but there are also alternative computational approaches, such as reweighting the images and also adjusting for your data set bias in comparison with some other data sets. And so the image on the right here, as you can see, this is actually our default face at 0, 0, 0, 0. So the image that we use on Juntos is not at 0, 0 because of stability issues. But you can see, that it's like every data set is going to have that kind of opinion. Okay, and with that being said, I'm going to open it up for Q&A, and also if we want to bring back our moderation and stuff, so maybe we're going to stop talking now.
Yeah, if anyone has any questions, you can just put it in the Q&A or in the chat, and I'll read them aloud for our speakers today, and they can go ahead and answer them.
Well, I think I see a question about the hardware we used, Alex. I think you might be able to address that one in the chat.
Oh yeah. Okay, so in the chat, it's asked, what hardware did you use for Project Juntos? Can you redo it with Colab Pro, just one GPU, et cetera, et cetera, et cetera. And so for a project like Juntos, we use Amazon's like cheapest GPU option. So it's like even worse than like the P100. I think it's a K80. Sorry, this to get specific is like the P2 instance. So this is on comparable clouds. It's the type of hardware that costs $1 per hour. And yeah, I think it took only a few hours to retrain our linear map. Although if we wanted to retrain the GAN, it would probably take a couple days.
So was that software like part of AWS services? Yeah.
Yes.
Okay. We have another question. Colin asks, could we compare GAN with other similar technologies that I guess could be used for Juntos?
Yeah, and I guess I'll give this one to Eric, but maybe Colin, if you have a like specific application in mind, that would also be helpful in doing this comparison.
Yeah, definitely agree with Alex on that point. So the way I sort of think about GANs is that you sort of have a base set of data you want to sort of generate more of. There are other approaches that might feel similar, like variational autoencoders and that sort of stuff, which also can help generate data. But typically there's some sort of like function that, or some sort of metric which you use to sort of determine whether something is similar or not. So it feels like, at least to me, it feels like GANs are a little bit more open-ended, where you just need the data itself and present that to the GAN. And hopefully the GAN will do a good job of learning exactly what needs to go in and what doesn't. Like for example, with Juntos, if we were to try and not use a GAN, we might need to sort of come up with like a handcrafted metric for what counts as a realistic human face. And that's much harder, I think, especially in the case that we were trying to do. Things do work in. So yeah, I guess circling back, it will definitely depend on what you're trying to do, what you're trying to generate, and what you know. So yeah, once again, like ML is all about context, really. But yeah.
I'll just quickly add on. I think recently VIEs, which is another type of model, have become much more powerful. And so usually the trade-off was VIEs give you like more clean latent space, like the attributes are more cleanly separated and less correlated, whereas GANs give you much more better realism. But that's starting to change. So literally what I do in these kind of situations is I go to like papers with code. I find like the best recent models that have their like a good GitHub repository, and I try to use that.
Thank you both. We have another question. Have you had a chance to use your model in a real situation?
Okay, I see. Is this so? I basically for us this has been more on the project stage, kind of like prototyping as an idea. So we haven't like used it in the real world, I guess, to do like whatever, like forensic sketches or whatever. But I think as you can see from the images that are generated, I think a lot of those faces could definitely fool myself if they're outputted. And so yeah, but I'm not exactly. I feel like if you want to expand on that question, that'd also be helpful.
Yeah, I guess my add-on. Personally, I think the faces that you can generate, there's a wide variety of faces that are possible. I think that's really cool to sort of see, especially in a short-term project. One of the sort of other things I've noticing though is that oftentimes you'll see like the background of these faces being warped a little bit. So in terms of like generating like completely realistic photos in something on a larger scale, maybe Juntos isn't there yet, but at least in terms of generating faces that are like believable, and like I think we've also like manually tested a couple of cases where like trying to like emulate celebrities or like important figures and that sort of stuff. We were actually able to get pretty close and feel good about that. So definitely some room to improve, but I think it's already like pretty far there. So yeah.
I see a question a little bit up above about GANs using beyond image synthesis. Okay, I can just maybe quickly read it since I'm already looking at it. So they're just wondering, can we use GANs beyond image synthesis to generate mathematical graphs, or like let's say mass spectrometry graphs, or even music or voices or text? So I think the answer to all those questions is actually yes. You just have to be sensitive about the way you parameterize it. And so I've actually definitely seen GANs for music and voice. I wouldn't be, and also for 3D shapes. So these are all possible. And, I mean, in a sense, because all of those medium, their natural continuous like media can be distilled essentially to, a latent space. Like, and if our human brains can do it, there really isn't a reason why a GAN couldn't distill something into those attributes. Although definitely these things come with varying levels of difficulty. If I was trying to generate mathematical graph, then I would try to find a model architecture in the GAN, maybe that was good at handling, let's say, things in the frequency space. If you're doing something like, mass spec, where that can be like a more natural domain for your image. And so GAN is kind of like, this framework of how you use two neural networks. But ultimately, the neural networks you use, I think, will dictate whether or not it'll work well.
Yeah, great. I see another question. We don't need to separate data sets for GANs into training and test data. And sort of the answer to that one is yes. There's no need to sort of separate data into training and test data, because essentially the input data isn't actually really used in like a supervised manner. You don't need train test val split. It's mainly to sort of seed the GAN with a data set of realistic images, or like the images you want to sort of emulate. And so essentially this is only fed to the discriminator part of the GAN, and the generator is essentially the part that needs to learn the discriminator's, I guess, tricks unsupervised. So yeah, there's no need to sort of separate that.
Sorry, yeah, go for it.
I know we have a new question in the chat. It's kind of a long one. There are some shorter ones from Q&A that have come up, whatever you guys want.
Yeah, let's tackle those. So I think Colin asked, regarding comparing faces, are there test results, like what % correct? Or do you have test results that tell you, what % of time your GAN is correct? And what are the future potentials of GANs on this type of application? So I guess the first one, I think, goes back to Erich's answer, which is that it's hard to say like what % is correct. Like the only thing you can really test is your discriminator, right? Because it's impossible to say whether your generator is like correct or not. Your discriminator has like a correct percentage, but essentially it will be static during the entire training, because it will improve its like judgment abilities as your GAN improves, your generator improves its fooling abilities. And so it's not a very meaningful metric. At the same time, though, you can measure how well your discriminator does against like the real world data. So that's definitely a metric you could use. And just looking to the future, I think, yeah, GANs have a huge potential on this type of application as they become more and more interpretable and customizable. I think that, essentially all those things that we said in the next step will like become realities in future papers.
I think we have a question from Patricia asking about potential next steps for training and practical application of Juntos. And I think that's a really good question. I think there's definitely, especially for the use cases we talked about in the beginning, such as like reuniting children or doing forensic sketches, there's a lot of potential there. If I were sort of planning out this in the future, there are definitely a couple of steps I would first take. So one, maybe making sure that the Flickr data set we're using is a bit more clean. There are a couple of edge cases which Alex and I discovered recently, where there are people's hands or inside the images used in the Flickr data set. And so it's possible with a little bit of nudging and twisting to get people's like hands all up in their face and all that. And it's a little bit startling at first until you get used to it. So there's a little bit of cleanup work to do there. And then I guess, yeah, I guess, making sure tuning the model to better fit the needs. And then also, I guess, like working on UI design, that sort of stuff. So it's easier and more compact to use. Alex, do you have any thoughts on that or?
Yeah, I think definitely you also want to get ideally like feedback from your users. And so like discovering edge cases where your GAN did poorly is also a really good way of like troubleshooting it in the future.
Yeah, sounds good. And I guess when the GAN does poorly, like maybe it's like a case of where you can't really reconstruct the face you want. But that's great because then you can actually take the fill you're missing and augment your original data set your GANs trained on. And so hopefully the GAN can also grow dynamically like that. So yeah. I see another question about using style GAN2 ADA to generate abstract art images. And for some reason, the interpolation of these different, the latent space shows smooth changes of images. And so why are the changes here smooth instead of rough jumps? And so I think this is essentially a nice property that comes from the idea of latent space. So if you remember back in like that sort of chair latent space we mentioned, all these different chairs are distinct, right? They're like distinct objects, and they have special properties that we can just sort of measure and like be sure of, right? But for some of these attributes, like let's take rotation angle, for example, right? There's like some sort of natural interpretation of what that means. And so, once we're able to convert these different features directly into specific vectors in the latent space, because you can scale vectors smoothly as much as you want, there's some sort of natural transition of what it means in terms of the image as well, right? Since we've learned the mapping from the latent vector to actual images. And so I guess a weird side effect is like for things that are more discrete, like maybe number of likes for a share, that's something we think very discretely as well. But because we've essentially learned a vector that represents that, it is now possible to have like a 0.5 alike, which sounds weird, but it's like essentially a side effect of what the GAN does with latent spaces.
Yeah, this is like a pretty deep question that also goes into like how like your theory of like how neural networks work. I mean essentially, just to bring back some idea of what a neural network is doing, you're going from an image that let's say is 200 by 200 by 200, so that's 40,000 in dimension. And let's say you're compressing it to like a 500 dimensional plane space. And so what neural networks ultimately, what a good neural network does is that it will take like, let's say you're trying to classify these attributes, it will separate like all the noise in your image, the background, the rotation, the translation, let's say a face, and only distill like the actual essential features. And so like almost every neural network that we know of, is doing this like feature compression. And so naturally, like that's why, if you interpret this lane space, like if you had a really big lane space, it might not actually be that meaningful, like what the vectors correlate to. But as you get smaller and smaller and smaller, the neural network should be picking up the most salient attributes of the image towards your like classification goal. I don't know if that was very helpful, but it's like, and then okay, let's also there's a question asking how you would tell if the image is created by GANs. So this is very difficult, and was the subject of a huge kind of competition held by Facebook to detect deepfakes, which is very big problem for society. And ultimately, it's like it's basically like like a war almost, or like a race, in that like for every best like discriminator, there you can make a better like generator and vice versa. And so ultimately, companies that hold like the best like generator and discriminator pairs will probably have the easiest way of telling if an image is fake or not. At the same time, I know Eric might know about this, but you can also use computational photography methods to tell whether an image has been doctored. And so, for example, you can look at like JPEG or compression artifacts and other kinds of things to try to look for that. But I'm not sure if that applies to GANs, unfortunately.
Right. I think that's an interesting point you brought up. I guess I won't go into all the details right now, but it is possible to sort of take images and do a Fourier transform on them and look at the sort of distribution of the coefficients there. And typically natural images tend to follow some sort of natural pattern distribution. And so you can actually try and use that and use, I guess, slightly unintuitive methods to sort of tease out, which images are doctored, which ones aren't. And so, yeah, there's a lot of work there. So definitely would encourage you to sort of read up on that. And also, if you're interested, do some work there as well. So, yeah. I see a question on whether we want to consider applying our model to different races to increase the efficiency or effectiveness of our model. I think that's a good point. Definitely having diversity within some sort of initial training data set is going to be useful. Like if you, for example, like see a GAN with like everyone of like only one race, you're probably not going to get, people outside of that race represented very well. So part of this is like a data issue. But I guess also it's a little bit of a touchy sort of subject, because especially in like areas of application and industry, you don't want to sort of run into sort of discriminatory issues. So, definitely this is like a very important topic.
All right, thank you. Do we have any more questions closing out?
I think we have one more. Let's see, it says, yeah, so the question is, why do GANs work very well on some images, such as like anime, but maybe not on other different types of images? And if there's any sort of patterns to which images GANs work well with. And personally, I haven't really worked with like anime-based GANs. I think there's some amazing work though, like I've seen that in play a little bit. My personal guess is like, it comes down to the classification and description of each face. I think, especially with anime images, like there's some clear features that sort of describe well exactly what type of face you want to look at. But when we're dealing with like textures or rocks, I think it's a lot more fluid. So that maybe that's impacting it. And I also think a lot of this will have to do with the individual neural networks used to actually, further generate a discriminator. So it's probably a case by case basis there. Alex, do you have anything to add about that?
Yeah, let's see. I don't think there's any like one like field that is like unconquerable by GANs. Definitely think, ultimately like these generative models are improving every day. However, like for example, here's one thing. Okay, so like a lot of times the structure of your discriminator will really affect like the types of things your GAN pays attention to. So let's say you're trying to do a GAN that synthesizes like horses into zebras, right? So this is what CycleGAN does. And you are really concerned with, I want to keep the shape of the like animal, but just only change the texture. And so what they did in that paper was to use a patch GAN, which is a patch discriminator. And so this would run the discriminator classifier on like several patches of the image instead of on the image as a whole. And that made it pay attention to the more fine textural details as opposed to the detail of the animal as a whole. And so if that makes sense. And so I think you have to think about like, okay, how can I make it easy for my model to like learn the right things? Like, am I creating, is it incentivized to do this in the training, right? So you can add losses such as if you're doing this like domain transfer thing, you can add a loss like, oh, I want the structural the image to have high structural similarity, or I want like the color palette to like be the same, right? And that's going to, I think, make a big difference on how the GAN does.
Yeah, I think that speaks to the importance of knowing the context of what you're trying to do, right? I guess building on top of that, it is possible to sort of like hard code bits of or like seed and fix certain weights inside a neural net. So it is possible to sort of like force your neural net to be aware of certain things. Like I know, I mean, in one of my research projects, not related to GANs, we had an idea of essentially having part of a neural net dedicated to just doing fast Fourier transform on image inputs, which is very interesting, right? Because that's not something that like a neural net will sort of just magically learn by itself unless you get really lucky. So yeah, definitely, you know, drawing the GAN's intention to specific things you value is definitely going to help out depending on what context you use. So.
All right. Thanks for your questions, everyone. Do we have any final questions, final remarks? All right. That's the case. Thank you so much to Alex and Eric for visiting us this weekend. We really learned a lot from you, and we hope to discuss GANs later in the future. And I'll be ending this webinar soon if there are no more questions. And I'll see you guys next week. All of the regular attendees, that is.
Yeah.